The way in which it works is you establish goals and constraints, you teach the computer right from wrong through examples, and then you allow the computer to dream, to think, and to come up with alternatives. So let me show you some examples of this. This is a very simple example of a machine learning algorithm that is teaching itself how to play this game called Breakout, an early computer game. What it's told to do is very simple. Simply move the paddle and try to maximize the number on the upper left-hand side. That's the only thing it's asked to do. And so it starts off, and it's crappy, it's terrible, and then it plays again and again and again. But because it can play in computer time, it plays several 100,000 and then millions of games simultaneously. In the course of an evening, it plays more than all human players have put together, and of course becomes the best player ever in an evening. That's astonishing. Oh, and by the way, that algorithm can be applied to other types of video games as well. So what happens, what's different about these? What's different is that the very nature of the computation is represented as a neural network. It's a series of nested hierarchical structures. Well, essentially, you create this one complicated equation and representation of the thing that you're trying to solve. The thing about this is it's once you've created it, human beings can't unpack it. It's too complicated. Now, the applications of this is pretty interesting and pretty astonishing. So if we wanted to design a lighter, stronger chair, we would begin with a chair, an outline that looks like this, and then with a little bit of computation, it would analyze the chair, figure out its strength, its weaknesses, its tensile capabilities. The computer would generate an option, okay? It knows its goals and constraints, and then it represents or calculates how well it does against that. And then you have it do it again and again and again, and you wire it up to do 10,000, 100,000, a million, 100 million versions of it, and then plot the various alternatives here on a large cloud map, and then you play God, and you select the trade-offs that are important to you, and then you select the chair that has the property trade-off that you think are the right ones. And once it's done, you press print, and voila, you have a 3D printed chair. The implications are pretty interesting because you produce an outcome that might be a third the weight. It's not a very attractive chair, is it? It's not very comfortable. So what if, and this is today's algorithms, to design a beautiful chair? What if you could, in this algorithm, we optimize for certain aesthetic qualities and as well as the performance qualities. This is what it's thinking about. This is what it's beginning to calculate over and over and over again. And the end result is this. So be aware of what's happened here. Nobody has designed the chair. The two designers have given the goals and the constraints. Got to be this high, support these kind of people, got to look good, and it's been manufactured out of wood. And that's the end result. And by the way, these are the two designers. The woman on your left has never used this program before and never made a chair before. And after a couple of weeks, our artist in residence has fabricated that. Isn't that interesting? Isn't that phenomenal? So design a stronger and lighter suspension part here. So in commercial activities, this is called an upright. It's part of a suspension system. And so here the engineer is given the constraints, so where are the bolts that it needs to pass through. And then in this point, the computer generates the internal structure. This is called a micro mesh. And so it tries to make it as light as possible. And the end result is the one on your right. So the left is the traditional, the one is on the right. The important thing about this is the microstructure and what the microstructure actually emerges as. It has the same structure as bone. Literally, we have evolved it. We've used genetic algorithms, and in no way have we programmed it to create a bone or porous structure. The computer discovers it because it's the fittest response. So in the time that it's produced this, in the course of just a few minutes, it's gone through the equivalent of many millions of years of evolution. This is the start. So what if you wanted to design a better office space? This is our new office space in Toronto. We're moving in April. We have 3 stories at the corner of university and college. It's a great location. And so, of course, we want to have this as a beautiful and as vibrant space, and we want everyone to be as satisfied as possible with the space. So how do you do this? Well, you identify the 6 key goals that are important to people, the closeness, the work style adjacent to work teams, and then you allow the computer computer to generate alternatives on the floor plans. It looks like this. You begin with the constraints, the outline of the building, where the various meeting rooms are, where the kitchen is, and then from there take the and it formulates those. From there, you generate the various goals, and then generate renderings of the goals or examples of the goals, multiply them and unfold them. And then you evaluate, so how effective is each and every one of the alternatives in lighting and in heat and adjacency and so on. And from there, it produces many thousands. You take the very best 10,000 alternatives, and then they're organized into a system that you have various trade-offs. You select the trade-offs, review them with the people. There's a whole other part of the story with virtual reality and so on, so you experience it before it's actually done. And voila, you have a system that hopefully optimizes a very difficult and complicated problem. And so in April, we'll have the first taste of what this actually looks like. So I think about this point, you're beginning to encroach on what's called the ook factor, or I'm getting a little uncomfortable here because, isn't this encroaching on human creativity? I mean, isn't this what we do best? Aren't we people that envision new alternatives? Well, this is something that I think you'll find very interesting. What if we take something that is among the most human of capabilities, such as the creation of art? So machine learning algorithms were used to try to recreate a Rembrandt, a new Rembrandt. And many of you may have seen this before. And so how would you apply machine learning towards this? Well, you would begin by looking and studying every single Rembrandt. You would look at the facial features, what the eyes look like, where the shadows are, where they're looking, what the fuzziness is on the particular eyeball, and compare and analyze, and you begin to formulate a language of Rembrandtness. And then from there, you would take those features and see how they fit together and how they form entire compositions. And you evolve the feeling and the qualities of Rembrandtness. And from there, you go even more deeply into the brush strokes and understand how the paint has been layered up into the various structures, working it into something called a height map. And the combination of this evolves I see someone looking like this. And you begin to analyze this and create an underlying deep computer model of the essence of this great master. And then from that model, you give the goals and the constraints. Here are the goals. Let's make it a male, 30 to 40. He's wearing a hat. It's got a collar, looking right. That's the input. And here is the output. Let's take a look at that more carefully. Isn't it amazing? What would Rembrandt think if he saw this? What would an art expert look when he or she would see this? And what they do think and what they see is, it's a Rembrandt, but it's not. And it begins to blend boundaries and diffuse the traditional categories of what is art, what is authenticity, what is human creativity. So this is the beginning. Oh, by the way, you take the same algorithm and you can do it to Monet to get the essence of what is Monet and so on. It's the same fundamental algorithms.